Hello everyone, my name is Chandranil Chakraborty and I am going to present our work on improving the accuracy, adaptability and interpretability of SSD failure prediction models. I am from University of California, Santa Cruz and I am advised by Professor Heiner Litz, who is also the co-author in this paper. The use of SSDs has skyrocketed in the last decade for cloud computing services. Looking at the figure on the right, you can notice the sale of SSDs have been rising steadily, whereas for hard disk drives, it is falling. SSDs offer many advantages over traditional HDDs in terms of lower access time, energy efficiency, and due to lack of moving parts, it is highly portable and reliable. However, even being more reliable than traditional HDDs, SSDs wear out non-linearly with device lifetime and accumulates bad blocks over a period of time, which can result in unstable system performance, loss of data availability, or even data loss, which can be very costly. Predicting near-time failure trends helps to inform the device acquisition process, enabling to save costs and avoid capacity bottlenecks. Now, predicting SSD failures is an inherently challenging problem due to class imbalance. SSDs fail rarely, and hence the number of data points from healthy drives far outnumber the data from failed drives. In our dataset, out of 30,000 drives that we examined, only 4,000 failed at some point. A fraction of the drives were replaced and put back in production. The delay in repairing a drive lasted up to a year, resulting in even fewer data samples from the failed drives. As a result, the dataset contained over 40 million data points from healthy drives, while only 15,000 data points for the failed drives, identified as inliers in the figure in the right. In particular, the write patterns, random or sequential, and the read-write ratios affect the lifetime of a device considerably. Reasons leading to failure are highly application and device specific, rendering failure prediction by a simple universal technique virtually impossible and challenging task in general. Prior work on SSD failures has focused on studying the characteristics of failures in a data center environment and its correlation with UECC errors. Prior prediction work in SSD failures used random forest logistic regression, k-nearest neighbor, support vector machines, and decision tree based classification techniques to predict failures. However, the work suffers from three main shortcomings. Firstly, the overall limited accuracy for predicting failures. Secondly, the inability of reliably predicting failures which are not seen during training in dynamic environments, and the lack of interpretability of predictions. Compared to prior work, first, we provide a comprehensive analysis of machine learning techniques to predict SSD failures with highest recall and accuracy for both majority and minority class. Particularly our one-class autoencoder improves accuracy up to 13%. Second, we show how one-class predictive models can predict unseen failure types in a dynamic data center environment. Thirdly, we propose one-class autoencoder, an approach to interpret predictions of our model to enable understanding of the most important reasons for failures. The key idea is to train the models on the majority class while ignoring the minority class. It prevents the model from overfitting to the set of known failure types and improves generalizability of the models as it can detect unseen failure types not seen during training. Additionally, we introduce feature selection for selecting the most important features contributing failures and perform extensive hyperparameter tuning to find the most suitable parameters for the models. Overall benefits of using our approach over prior work include better prediction performance by up to 13% and the ability to predict failures in dynamic environments where the model is able to predict unseen failure types not seen during training. Additionally, since we do not include any data from failed drives during training, the model do not conform or overfit to the same set of known failure types, and the prediction performance improves with more data from healthy drives. The models also take lower training and inference time due to lower dimension of input features. For this project, we analyzed data from Google for over 30,000 drives in the data center for a span of 6 years. The data set included approximately 40 million reports and 4,000 failures. Each report included 21 features collected, including drive characteristics, status flags, and error counts. Some failed drives were put back into service upon repair, which we treated as a separate failed case. There were three models of SSDs in the dataset with no information of vendors. The spread on the type of SSDs in the population is shown in the table below. Our feature selection technique, which we will explain later, did not select the model name as a top distinguishing feature, hence it was eventually dropped during training process. The slide shows all the 25 features that were collected per report, and we used feature selection techniques to filter out the top 9 features. We used 3 different feature selection methods: filter, embedded, and wrapper techniques, and implemented 8 different algorithms, including Pearson ranking, Spearman ranking, chi-square test, ANOVA, recursive feature elimination, extra trees classifier, and regularization techniques to find the most important features. The top selected features are reported on the table right. For imbalanced datasets, the traditional metrics, accuracy, precision, recall, F-score alone, can be deficient in measuring the performance of the classifier. Since the dataset is imbalanced, overfitting to the majority class, that is predicting all observations as the majority class, can skew performance and still reflect good overall precision, recall, and F-score. The ROC curve is a graphical plot that illustrates the diagnostic ability of a binary classifier, as it is a discrimination threshold is varied. The area under the curve, known as ROC AUC, is calculated to give a single score for a classified model across all threshold values. We use this metric to compare our performance with baseline approaches. This is also in line with prior work, which uses ROC AUC metric for comparing predictive performance. Now, from the table we can see that our isolation forest and autoencoder based one-class approaches displays better performance in separating the failed drives from the healthy ones. The autoencoder in particular achieves the best performance, outperforming the best baseline technique by 7.6%. Here we show the accuracy, precision, recall, and F-score comparison for 5 evaluated machine learning techniques. Precision is shown in yellow, recall in red, and F-score in green. Here also we can see our approaches trained on the majority class outperforming the prior approaches. One class autoencoder in particular outperforms the random forest by 9.5%, whereas one class isolation forest outperforms the best performing baseline by 7%. Random forest, the best performing baseline, performs equally well for healthy drives, but considerably worse for failed drives. Here we show the improvement by using our approach in predicting unseen failures. The figure shows the ROC AUC score for 3 baselines and our proposed one-class techniques with a variable percentage of failed drives included in the training set. We sweep the number of failed drive observation included in the training set from 10% to 100%, simulating dynamic environments where new failure types emerge over time. Note that our one-class techniques do not include any failed drives in the training set, hence we plot the performance as a straight line. Now we can see that the baseline performances, however, depend significantly on the number of minority samples in the training set. Example, in particular, if only 50% of the failed drive observations are included in the training set, our proposed autoencoder technique outperforms random forest by 13% and neural network and SVM by 33%. This shows that in particularly dynamic environments, our one-class techniques are a better choice than techniques utilized in prior work. This work proposes one-class autoencoders for interpreting SSD failures. In particular, our techniques expose the reasons determined by our model to flag a particular device failure. This is achieved by utilizing the reconstruction error generated by the model while reproducing the output using the trained representation of a healthy drive. The failed drives do not conform to this representation, thereby generating an output which is significantly different from the actual observation, producing a large reconstruction error. We study the reconstruction error per feature to generate failure reasons. The features which contribute to more than the average error per feature is defined as a significant reason. The figure on the right shows how often a feature was flagged as a significant reason by the autoencoded model aggregated for all observation from failed drives. The y-axis displays all the features utilized by the model, and the x-axis shows the failed drive number. From the figure, we can see that the many failed drives show a higher than normal number of correctable errors, counting the number of failed reads that could be corrected leveraging the error correcting codes. This indicates that a high number of uncorrectable errors frequently lead to failures. However, it's also a significant feature in approximately 37% of the cases. Cumulative bad block represents another important reason determined by the model indicating SSD failures as it shows frequent anomalies. However, again, it's only present in less than 30% of the cases. In summary, this analysis shows that there exist particularly relevant features that indicate failures. However, only the combination of several features enables accurate prediction. Now, to optimize drive maintenance and acquisition of new spare drives, it is preferable to predict drive failures further ahead in time. Now we discuss the impact of predicting ahead in time. As expected, for all 5 models, prediction performance degrades when we predict further ahead. But while for one class autoencoders, the performance degrades considerably, and along with the others, baseline techniques included, the one class isolation forest can maintain the performance better. This can be seen in particular for n equals 4, that is when we are predicting 4 days ahead of time. The one class isolation forest model becomes the best performing technique, outperforming the random forest baseline by 6%, the SVM models by 11%, and the neural network based models by 13% correspondingly in terms of ROC AUC score. Now let's discuss the impact of feature selection technique in more detail. So from the figure on the right, you can see that every technique, including the baseline techniques, benefit from feature selection in terms of ROC AUC score. For our one class models, we can see the autoencoder benefits more, autoencoder based models benefit the most by using feature selection. And the table on the left shows the benefit in terms of training time using feature selection. So you can see that feature selection can reduce training time by up to 1.8 times. So based on this, we can see that feature selection optimizes the SSD failure prediction process by essentially providing a lower dimensional relevant input data. To conclude, our work provides a comprehensive analysis of machine learning techniques to predict SSD failures in the cloud. We show that our approaches based on one class machine learning models can outperform prior work by 9.5% and in terms of ROC AUC score by significantly improving the prediction accuracy for the failed drives. For dynamic environments, our one class techniques improve over the baselines by 13%. We also show that the one class autoencoders can enable interpretability of model predictions. Thank you for your time.